Hi everyone, welcome back. Wanted to do a second video on the Nernst equation and specifically wanted to talk about how we use the Nernst equation to measure pH. So this is a really nice application of the Nernst equation, and it'll kind of relate back to our acid-base unit when we talked about how we measure pH using a pH meter. So it turns out that the use of a pH meter is essentially based on the theory of how the Nernst equation works. So just to review, here's our Nernst equation. So we know that, of course, E cell equals our E cell standard minus 0.0592 volts over the moles of electrons times the log of Q. So there's our Nernst equation we talked about in the last video. So now what we're going to focus on is using two half reactions. So we're going to use the hydrogen half reaction and then some reference electrode. Which we'll talk about in a moment. So we're going to focus first on the hydrogen half reaction, and you can probably see right away that by using the standard hydrogen electrode, we're going to be able to relate that to pH or H3O+, because we have this H+ component in our standard hydrogen electrode. So let's just say that we have E hydrogen. So we're going to think about what would the Nernst equation look like if we just focus on the hydrogen half cell. And we know that that would equal standard cell minus 0.0592 volts for N. And our hydrogen half reaction, let's write that out just in case you don't remember. So we have hydrogen gas oxidizing to form hydrogen ion plus 2 electrons. And so we know then that we would have log of H+ squared over pressure of hydrogen. So that would be our Q expression. And we know that E cell for the hydrogen electrode equals 0 volts. So we know that from our standard reduction potentials. So either the oxidation or the reduction, we basically have identified that as 0. That's our definition. So we know then that E hydrogen equals 0 minus 0.0592 volts over 2, because we have 2 moles of electrons in that oxidation. And we know that we have a pressure of 1 atm. So we can essentially say then that we have log of H+ concentration squared. So we can ignore the 1 atm. It's just factors out. And now we can say E hydrogen 0.0592 volts over 2 moles of electrons. We can use our log rules, so we can pull the 2 out front. So we know that we have 2 times the log of H+. Now we can see that these 2's will cancel. And then let's rearrange. And we can say times the negative log of H+. And of course, you know that the negative log of H plus is pH. So we can then say this. So we can hopefully clearly see that using a Nernst equation, we can quickly use that to come up with an expression that relates pH to our electrochemical system. So remember, this is only the half reaction that includes hydrogen. We also have a reference electrode. So we can say then that the total cell potential, and we can consider this to be the solution, right? So we're going to consider the total cell potential be, say, some solution we're measuring is going to equal E of hydrogen plus E reference, right? So if we have these two half reactions involved in our electrochemical cell, they're going to add together to give us the total cell potential. And then, of course, we can plug in our E hydrogen expression that we just created to give us that. So we have E cell, we have our pH, we have this reference electrode. So let's rearrange all of that, and we can say then that pH equals E cell minus the E reference divided by 0.0592 volts. All right, so it turns out that a typical pH meter uses this silver electrode, sometimes called the glass electrode, because it uses glass as kind of the membrane to separate the reference electrode in the solution. And so this glass electrode has the following reaction. So we have 2 silver, which is of course a solid, plus 2H plus produces silver ion plus hydrogen gas. So that's the overall reaction in dilute HCl. So what we can imagine then, hopefully, is we could find the potential of the reference electrode. So that would just be determined experimentally. All right, so we would know the voltage of the reference electrode. We know the potential of our hydrogen electrode, right? We know that is 0, and we've used it to then relate to pH. And so that's where the pH comes from. That comes from our hydrogen electrode. And so what we do is we dip this electrode into an unknown solution. And so the E cell is basically the potential of the entire solution. Right, so that's measured experimentally. And then of course we know the E reference. That's determined prior to creating the pH meter. And so by comparing that potential of the entire unknown solution and knowing the reference electrode, and we just divide that by 0.0592 volts, that then yields for us the pH. So what you can imagine is we have an instrument where we have basically a electrochemical reaction taking place in the solution, right, with this electrode immersed in the solution. And we just get electrical signals, right? You get an electrochemical signal, this potential that we can measure, and then we simply calibrate the electronics of the instrument to then read out what the pH would be. So if we were to take a known solution, right? So we could take a solution that's either neutral with pH 7, or we could create an acidic solution with a very specific pH, knowing the concentration. And then we can then calibrate the electronics to read out the correct pH. And then when we put this pH meter into a new unknown solution, then the pH reading that we get should be fairly accurate in terms of what the actual pH would be. So hopefully it gives you at least a little bit of a sense for how the pH meter works. Trying to appreciate that this is essentially based on the Nernst equation, and that when we use the Nernst equation with the hydrogen standard reference, standard electrode, we can use that to extrapolate out pH. So I hope that helps. So what you can do now is try this question. So here, this is an older style pH meter. So the new style pH meters, the one that you used in lab is most likely this glass electrode, where it's the silver chloride reaction that's taking place coupled with our hydrogen. So whatever hydrogen ions are in solution. And then this is an older pH meter called the calomel reference electrode. So this is based on a mercury chloride. So as you can imagine, we don't use these electrodes as much because they use mercury, which we try and avoid due to the fact that we now know that it's got toxicity issues. But we can do this mercury reaction. So again, we have hydrogen reacting with mercury, producing H plus mercury liquid. And so hopefully if you go through your redox, we can see then that hydrogen is oxidized, mercury is reduced in this reaction. And the half reaction of mercury chloride forming mercury 0, that's potential is 0.28 volts, so plus 0.28 volts for that half reaction. And so knowing that, if we were to use this calomel electrode in a similar way, so imagine we take this electrode that's now got this mercury chloride system separated by a membrane, a permeable membrane. We measure the total solution, our unknown solution, the voltage readout is 0.55 volts. So based on that, you can determine what is the pH. So pause the video for a moment, see if you can determine that. And then when you come back, we'll go over that solution. Okay, so hopefully you were successful. So this is one of those questions where they often sound a fair bit more difficult than it actually is. So all you have to remember is that our pH is simply equal to the E cell of the total solution minus our reference electrode, which was given here. And you just divide that by 0.0592 volts. So the E cell, that's based on the potential that's observed when we put this probe in the unknown solution. That's the cell potential that we measure. And that's found to be 0.55 volts. We're going to subtract our reference electrode, which is this mercury chloride half electrode, half reaction, plus 0.28 volts, divided by 0.0592 volts. This is a case where all the units cancel, and we hopefully find that we get a pH of 4.6. So B would have been the right answer. So pretty straightforward calculation. The hard part was actually using a Nernst equation to derive the pH equation that we use here. So again, hopefully you appreciate now how we're using the electrochemistry to then do these pH measurements using these electronic instruments. It's all based on this electrochemical potential difference between the hydrogen electrode and whatever reference electrode we choose. And so again, the two most common electrodes are this mercury chloride calomel electrode, and more modern pH meters tend to use this glass electrode. All right, so I hope that's helpful. Gives you a little bit of context for use of the Nernst equation, and helps you give some appreciation for how we measure pH in the lab. All right, so we'll see you next time.